this is a second presentation of the verification of the physics constraint Gaussian process for the prediction of the life of same steel, ATMNI 300 Maraging steel, the MS1 steel from EOS under multi-action loadings. So basically the topology optimization of and mass reduction or heat transfer can lead to very complex extreme geometries, including unmachined thin-walled elements. And such geometries is obtainable with the additive manufacturing, with LPBF, laser power bed fusion technology. However, the inherent internal and surface defects may considerably reduce the fatigue strength of the unmachined elements. So the fatigue strength of the thin-walled unmachined parts obtained with the additive manufacturing and under multi-action loading was something we wanted to take a look at. So the fatigue strength determination of the thin-walled up to few hatch spaces, Maraging steel tubes was under various multi-action loading paths was the aim of the study, and also the efficiency estimation of stress-based approaches for fatigue life prediction in the case of this study was tested. So a few words about the material. Like I said, EOS Maraging MS1 powder. It's the 18Ni 300 Maraging steel. We used the same printer as before, and M280 from EOS. Here's the material composition from the supplier and from our own test from the spectrometer. They're quite the same within a range, I would say. Also, the particle size of the powder was tested, and the median was about 30 micrometers, when 90% of them below 47. So, yeah, I would say standard. Here are the specimens we used. We tested like hundreds of them. So it's a tube with a hole diameter of 5 millimeters, and the outer layer of the tested part, the smaller part, is 6 millimeters. So the wall nominally was only half millimeter in thickness, and a plate of some of them. All of them printed in the horizontal, like 90 degrees direction, every single one of them. The building strategy, the hatching strategy is shown in here. It was used the standard one from the EOS, so a few hatches. The next layer moved by 67 degrees, and again plus contouring on both sides. And the parameters are here. We paid much more to know them, so it's the standard EOS one for this printer. The mechanical properties are as follows. It was where H hardened for 6 hours and 490 degrees Celsius, then cooled with the oven, so another 2 days, and this is what the EOS recommends. Ultimate tensile strength up to 2 gigapascals, yield strength very close, 1928, Young modulus about 180 gigapascals, and the elongation of them after heat treatment. The last presentation, it was 13%, 11 to 13 basically. Here's this 2.7. It gets much harder, much less plasticity in it, and the hardness roughly 640 H-power. So we use this fatigue test from Instron. It's an electrical machine, 10 kilonewtons in tensile and 100 newtonometers of bending torque. For some of them, we used a bigger rudder of this machine, 10 times bigger, for the very high, very low fatigue life and higher stresses, because this wasn't enough. And we use 6 loading paths for the fatigue test. The first one is just tension compression, the second one only torsion, and in-phase combination of tension and torsion plus out-of-phase combinations. The tests were roughly between 300 to up to 200,000 fatigue number of cycles fatigue life, so low cycle fatigue. After the printing, we use a tomography to measure exactly the wall thickness and the void distribution of the printed specimens. The models we used to calculate the fatigue life, other than our Gaussian machine learning model, was the ones here. So Stulen, Cumming, Findlay, Crossland, Patake, Papadopoulos, and Papuga-Ruzicka. But instead, most of them use fatigue limit as the parameter. We used the dependent on life parameter because the characteristics were not parallel and the fatigue limit has some limitations. So we use the parameters that change with fatigue life. And the model that was the machine learning model and all the way we calculated everything is shown in simplicity on this slide. So we had the training data. We used only uniaxial fatigue for training data for our model. So only tension compression, pure tension compression, and only torsional. We didn't learn the model on multi-axial results, which we did obviously, but I mean, we did the test, but we didn't show it to them, to the model, our Gaussian model. And for the other models, there was from the signal from the test, we did the tensor of the stress, but in order to make it irrelevant to rotation, it was recalculated for these parameters that don't care in which direction they are. Then from the data, we took the fatigue life and calculate the training process as follows, with one physical constraint for the model that because the Gaussian model doesn't really know what it's calculating, so the results were quite different for the SN curves. So the only thing that SN curve had to be decreasing with fatigue life. I mean, if the stress was higher, the fatigue life should be lower, and on the other hand, if the stress was lower, the fatigue life should be higher. So that was the only one concern for the model. All the models that were waves or whatever were not taken into the account. And on the other slide, we have we used a pairs of verified input quantities. So the predictors I was showing later. Here, when the first one is the maximum normal stress and in the plane of maximum shear stress, then the maximum hydrostatic stress, the amplitude of the second invariant of the deviating stress tensor, and the generalized shear stress amplitude from Papadopoulos. And the pairs, except this one, there's no critical plane in this model, so there's no pair with the critical plane. Here's data from the tomography. This is not moving around. It's different layers. And last week when we did this video, this show, it looks like it's turning around. Yeah, and we have to investigate why that is. Maybe the laser starts in a different place or around, and maybe the imperfections are moving regarding to the starting point. We don't know. We don't know why it probably shouldn't look exactly like it's moving around, but it does. It is. And here are some voids. Basically, the porosity was not so big. It's 1.15%. And the surface detects, we also use the tomography to calculate the exact thickness of the wall, which was a little bit below 0.5. And as you can see, in all cases, array RZ and RV, the inner surface has a worse. It's worse than the outer surface. The The specimens were shot filled with glass in size of 90 to 150 micrometers, and it's much easier to shot fill the outer layer than the inner when the specimen was 8 centimeters long. So probably it's just not cleaned enough, because in the fatigue process, in most cases, the fatigue crack appeared from the outer layers. But we'll get to that. So this is the SAM samples. You could clear. It's not so great here, but you could clearly see the contouring and the hatching on the specimens, and the cellular structure with the hard particles within a soft martensite matrix. It can be seen here. Sorry, this is the same. And the cracks in like 90 degrees, 90% were from the outer layer, mostly in imperfections, like the valleys here of roughly 45 micrometers. These were the places where the fatigue appeared. And to the results, this is the training data. So push-pull, tension, compression, and torsional fatigue curves, they are not parallel. That's why we didn't use the fatigue limit for the models, just the life-dependent relations. And for Crossland criterion, you can see the training data and the multi-axial data. And for each loading path shown on the slides at the start, and the scatter for each one. So the Crossland, which was quite surprising, did quite well here, and very good for the third loading data. So one of the in-phase multi-axial test, not so good for the other. It's 3.1, and very good for the out-of-phase multi-axial fatigues, but because it's like only 2.3 the scatters here, which I will explain later why. On the other hand, the Papuga-Różicka criterion didn't work so good, maybe except of the first one. The fifth and the fourth one were, this one was very close to 4. The scatter was up to 3.9, and for the load 4, it was 3.1. And this is the Gaussian process. Like I said, it was trained only on the uniaxial fatigue, and we are showing the pair of maximum tensile strength in maximum tensile strength maximum shear stress in the and hydrostatic stress. Basically, all of the models that are, all of the pairs that were using hydrostatic stress, and all of the models that were using hydrostatic stress, so Papadopoulos and Crossland, did much better with this steel than the others. It's how it is, I guess. You can see it in this table when the average scatter for Crossland and Papadopoulos is 2.5, 2.6. Same for our model. It's much worse when there are 2 maximum shear and normal stresses. It's 4, but when there was a hydrostatic stress, 2.58, 2.59, as you can see here. It was surprising that we didn't have to train it on the multi-axial. And now we know it was just this one case, because this steel has very little up to 0 plasticity. Even in the plastic deformation, even in the fatigue life was non-existent. So it was much easier for the model to learn. When we use other steels and aluminum alloys later, it's not shown here. We had to train it on the multi-axial, just to clarify. It's not so great. And there's conclusion only. To summarize, the fatigue SN curves of H-hardened and unmatched thin-walled maraging steel tubes exhibited linear relations in log scales for wide fatigue range. Fatigue strength ratio was significantly varies in analyzed regime. Crossland and Papadopoulos classic fatigue models with light-dependent material were successfully applied in fatigue life prediction as in-phase and out-of-phase multi-action, and they both include hydrostatic stress. That was their main reason. The Gaussian process strain only on uniaxial and torsional loadings with predictors including hydrostatic stress and arbitrary shear-based stress were also successfully applied, and fatigue life tested patterns between hydrostatic shear-based stress and fatigue life, include uniaxial and torsional SN curve data. Thank you.
Okay, thank you very much for your presentation. We have time for one quick question. Okay. Yes, please.
Yeah, excuse me the uneducated question, but why did you use the data from a different loading scenario to train the model?
Because we wanted to predict multi-axial fatigue. That's why we use tension, compression, and torsion. When you do multi-axial, there are combination of tension and compression and torsion. So we had to start from somewhere. It always starts like that.
That I get, fatigue. But wouldn't there be synergistic effects between the different loading scenarios?
I mean, there are some, but there's a difference it's the pure states are always the start for multi-axial fatigue predictions. So it's like that. Just okay. You have to have, because the material is quite different in tension, compression, and you have to know at least what will happen in the pure states.
Okay, thank you.
Thank you.